Kiddos, welcome back. We have a few vocabulary terms I want to talk about today. Something called heat or enthalpy of fusion, or heat or enthalpy of vaporization. And after we discuss that, I want to talk about this heating curve for water. You may have seen it before. There's a demonstration that I have that goes along with this heating curve that I will refer you to as well. So let's just jump right into it. Heat or enthalpy of fusion is simply the heat or energy, we could say, required. So this is an endothermic process, kiddos. We need heat from the surroundings for this to happen, to melt a solid at its melting point. So when you get to the melting point of a solid by raising the temperature of the solid, the temperature doesn't change any longer, even though you're adding heat. The energy that you're adding is called the enthalpy or heat of fusion, and that's energy that's required to melt that substance. Then once it's all melted, then the energy that you add goes into raising its temperature again. But the energy required to melt a substance at its melting point is called the enthalpy or heat of fusion. What do you think the heat of vaporization is? Yeah, you're probably right there. It's the heat or energy required, so once again, an endothermic process to boil a liquid at its boiling point. So the heat of vaporization, the enthalpy of vaporization, is energy required to boil a liquid at its boiling point. So once you heat a liquid up to its boiling point, even though you're adding additional energy, the temperature of that liquid does not change any longer. It stays the same. The energy that you're adding goes into changing its phase from a liquid to a gas. It's pulling the particles. It's being used to pull those particles apart. As you can imagine, the heat of fusion and the heat of vaporization increases as the intermolecular force of attraction increases. So the stronger the intermolecular force is between molecules, the more energy or heat needs to be added to melt or to vaporize it. So let's take a look at this heating curve, or if you look at it in the opposite direction, it's actually called a cooling curve. So let's start with, pretend you have a beaker, and one evening you fill that beaker up with water, and you place a thermometer in that beaker. So far, so good. And you stick it in the freezer overnight. And then the next morning you get it out, and the thermometer says negative 25 degrees Celsius. It is cold, in fact. This is all solid, isn't it? It's all frozen to begin with. So you take this and you put this on a hot plate. So we're going to draw a picture of a hot plate here. All right, and we're going to plug it into a wall outlet, and we are going to turn the heat on. So we're going to turn it on to high. And as you turn the heat on, obviously the temperature of that ice begins to increase. So let's go ahead and change the color of our pen here real quick. And here we are on our graph. The temperature begins to increase, and it gets warmer and warmer and warmer until it gets to point B here on my graph. And then you'll notice something. The temperature no longer increases even though you're adding more heat for several minutes. Because what's happening? That's right. The enthalpy of fusion comes into play. The energy that you're adding goes into melting that solid at its melting point. So during this time, the temperature doesn't increase, but the phase changes. You go from a solid to a liquid, and then you finally get to point C. And what happens at point C? Well, the temperature starts to go up again, doesn't it? How come the temperature starts to go up? Well, the phase change has been completed, and so now it's all in the liquid phase. So the energy that you now add goes into increasing the temperature of the liquid. So during this time of the heating process, you now have all liquid water. The solid is gone. It's all melted and it's changed phase into the liquid phase until you get to point D, which for water is 100 degrees Celsius. We call that the normal boiling point for water, and the water begins to boil. And the temperature, interestingly enough, does not change again. Right? Why doesn't it change? You're adding heat. Shouldn't the temperature go up? No, this is where the heat of vaporization comes into play. The energy that you're adding goes into changing the phase. It's pulling those molecules away from each other and turning them into a gas. Notice that the heat of vaporization is bigger, takes more energy, than the heat of fusion here, which didn't take as much energy. That should make sense, because in the heat of vaporization, aren't you separating the molecules from the liquid to the gaseous phase and putting huge distances between them? But when you're melting it, that's not happening. You're breaking that crystalline structure, but you're not putting huge distances between the molecules. So the temperature doesn't change. Now, it's here where I have a demonstration for you. I boil water in a paper cup. And you would expect the paper cup to burn. And it doesn't. I heat it over a Bunsen burner. Something interesting happens here, and it has to do with the heat of vaporization of water. So you'll be watching this demonstration in conjunction with this video. All right, then we get to point E. And from point E onwards, the temperature can go up because the phase change is complete. The water now is all gaseous, and we just increase the temperature of that gas as we add more heat. Now, notice when you go from the left to the right, we are adding heat. These are all endothermic processes, right? Melting and boiling require heat. What if you were to go backwards? What if you were to take a vapor, right, and condense it and then freeze it? Wouldn't that be then an exothermic process? Wouldn't energy be given off? Yeah, that's exactly what happens. When you go in the opposite direction, energy is released to the surroundings. And we call that a cooling curve instead of a heating curve. Alrighty? Okay, I think that's good enough. This is a pretty short video. Hopefully you have an understanding of what the heat of fusion is, the heat of vaporization is, and you understand a heating or a cooling curve. All right? Talk to you soon. Bye-bye.